Thank you, Tim, and good evening, everyone. And particularly thank you to the CIBSE ASHRAE group for inviting me to give this talk. Half of this presentation has been used before, but it's worth repeating because it's interesting and useful stuff. And the other half is a new perspective, which I hope you'll find useful as well. So the topics to cover, we're really talking about the road we've taken so far, the bumpy road as I call it, and then where we're headed to next. And obviously this is a very topical subject because there are lots of changes happening at the moment. So there's plenty to talk about. The road so far really splits into two lanes. In the world of chemical refrigerants, back in the 1980s, we were faced with phasing out CFCs like R11 and R12. Some folks will be old enough to remember using them, very, very good as refrigerating fluids, but identified as causing depletion of the ozone layer, so being phased out in the 1980s. HCFCs are things like R22, which became very much the mainstay, and in the 1990s, CFCs were really gone, and a new chemical called an HFC, hydrofluorocarbon, was being introduced throughout the 1990s. In the last decade, we've begun to see the phase out of R22, and it is now no longer permitted in use in Europe, and HFCs have become established as the mainstay of the chemical refrigerant family. And in more recent years, we've seen the introduction of another chemical called an HFO, which is a hydrofluoroolefin, also actually an HFC because it comprises of a carbon backbone with hydrogen and fluorine atoms attached to it. So the difference between HFC and HFO is quite small. It's that the HFOs have a double bond in the carbon backbone and therefore are rather more easily broken down in the atmosphere, have a shorter life and therefore less effect on the environment. In the world of what are called natural refrigerants in the 1980s, we were mainly using hydrocarbons and ammonia. In the 1990s, CO2 was introduced and began to be widely used, firstly in supermarkets, and then became used in industrial refrigeration as well. In the last decade, all three of these have become very well established in a variety of applications. And more recently, we've started to see water as a refrigerant being researched and developed, and I'll talk a little bit more about that later at an appropriate point in the presentation. One thing to point out about this is the natural refrigerants are not gathered from nature. They're things which arise in nature, hence the name natural refrigerants. But ammonia is actually one of the most widely manufactured chemicals in the world, produced in gigantic, high-pressure, high-temperature chemical complexes. About 180 million tons a year of ammonia are manufactured, so it's very much a process chemical, but it's a process chemical that occurs in nature. Whereas what I call the chemical refrigerants are synthetic, is another name used for them. Thinking about the chemistry that lies behind them, as I said, they all have a carbon backbone. I prefer to call them organic refrigerants. So we've got natural refrigerants and we've got organic refrigerants. As the chemists would say, they're all volatile organic compounds. If you're using an organic Rankine cycle, that's because you're using one of these HFC or HCFC fluids as the working fluid in the organic Rankine cycle. So organic refrigerants versus natural refrigerants. Now, in terms of refrigerant choices, it's really a balance of lots of factors. Some of these chemicals are very expensive to make. Some of them are very cheap to make. In the case of water, it's basically there for you. It doesn't need to be particularly special water. It's just water. CO2 and ammonia and hydrocarbons are relatively cheap. The HCFCs produced in chemical plants using a lot of energy, relatively expensive, and the new fluids more difficult to produce, more energy intensive, and therefore more expensive. But there's also a trade-off in system cost, that a system which can use relatively low pressure pipe or particularly brazed copper will be fairly cheap to install, whereas a system like a CO2 system requiring high pressure welded steel pipe will be a bit more expensive. So a bit of a trade-off there. The choice of efficiency and the operating pressure of the fluids and the cooling capacity of the fluids are factors which all trade off each other. So a high pressure fluid will likely give you a bigger capacity from a given size of compressor. You get very big capacity with CO2, which is extremely high pressure, very low capacity with R11, which is a low pressure refrigerant, because you need a much bigger compressor sweat volume to deliver the kilowatts of cooling. The two main environmental factors that are considered are ozone depletion, which was the subject of the Montreal Protocol back in the 1980s, and global warming, which has been the subject of the Kyoto Protocol in the 1990s. And in some cases, the refrigerants have an adverse effect in both. R12, for example, had a high ozone depletion potential, but also a very high global warming potential. On the other hand, fluids like ammonia, CO2, water have no effect on the ozone layer and virtually no effect in terms of global warming potential. And then finally, considerations of toxicity and flammability, also slightly more complex than you might think. Ammonia is a very obvious example of a gas which is both flammable and toxic, and therefore needs careful consideration in the design of systems. But all of the fluids, with the exception of CO2 and water that I'm going to talk about, are flammable. They can all be burnt, and in some cases they burn to fairly innocuous substances, and in other cases they burn to very toxic substances. So when we're considering flammability, it's a factor even for R134A and for R12 and for R22, fluids which are generally considered to be non-flammable. What that means is there is no spread of flame when they're ignited, but you can still burn them. And the toxicity question, the refrigerant itself may be toxic like ammonia, or the products of combustion may be toxic like R134A or R12, or the fluid may be completely non-toxic like water, or relatively mild like CO2, which is a very unusual toxicity but is considered to be generally non-toxic. It's part of our breathing reflex, and therefore if there's too much CO2 in the atmosphere, it interferes with our breathing and can cause asphyxiation at relatively low levels, but it's talked about as a non-toxic substance. So we need to be a little bit careful about both of these in terms of how good or how bad a fluid is, in simple terms. So I've devised a system of rating these very, very subjectively, just on a scale of 1 to 10, where 10 means it's a really good thing and 1 means it's a really bad thing, and then plotted them on this kind of target. And by my assessment, if I looked at R12, it was kind of middle of the road for cost, reasonably good for efficiency, works at a very acceptable pressure, quite easy to work with, gave a relatively low capacity, was very poor from the point of view of ozone depletion and global warming, relatively benign in terms of toxicity, so scored fairly highly, but just with that caveat about the effects of combustion. For example, somebody doing some brazing on copper pipe on an R12 system could suffer very severe poisoning from the fumes coming off the plant. And likewise, flammability, it's not entirely non-flammable, but it doesn't cause spread of flame, so I scored it kind of middle of the road. And you can see that basically R12 is doing a good job of filling the top half of the graph, but not so good in filling the bottom half. R22 is slightly better in terms of capacity and GWP and ODP, so it's beginning to fill out the bottom of the graph, but still about the same as R12 in the top half. And as we move on, ammonia, better in terms of cost and efficiency, about the same in terms of pressure, fantastic in terms of GWP and ODP, but the gas itself is toxic and the gas itself is flammable, so it scores fairly poorly on the left-hand side of the chart. Carbon dioxide, non-flammable, it's actually a product of combustion, so it has already burnt, so it's not going to burn again. Toxicity, as I said, relatively benign, but you need to be careful. Excellent in terms of GWP and ODP, there really is no effect. Gives extremely high capacity from a relatively small compressor, but works at very high pressure. So there's a challenge in terms of delivering plant at the pressure. But it's worth noting that CO2 and ammonia are very much cheaper than the organic chemicals that I talked about earlier, like R22 or the more modern ones. So it scores pretty highly in terms of cost, only marred by the fact that systems tend to be expensive. So although the refrigerant is cheap, the plant you have to put it in is a bit more pricey. Then moving on to hydrocarbons, very flammable, benign in terms of toxicity. You could even have scored that higher because the products of combustion are also generally non-toxic. Scores pretty well on efficiency. It's actually better than R12 and R22 and operates at similar kind of pressures, and obviously no ozone depletion potential. So you can begin to see a kind of pattern emerging that the old refrigerants filled the top half of the graph very nicely. They were non-flammable, relatively low cost and reasonably efficient, but they performed very poorly in terms of the environmental factors. R134A, which was the first of the HFC refrigerants to be introduced in the 1990s, gives a kind of different shape. It's not bad in the top half of the graph, a bit more expensive than R12, but about the same in terms of flammability and efficiency. But where it's a bit thin is at the 5 o'clock and 7 o'clock position, and capacity, relatively low capacity, and on GWP has a fairly substantial impact on the greenhouse effect, with a global warming potential of around about 1400 compared to CO2. So if we compare R134A with R12, you can see the difference in filling out the top half and filling out the bottom half with R134A. This is the essence of the compromise that we've been faced with for the last 30 years. We're having to move away from substances that were pretty good from the point of view of safety and efficiency to substances which are not quite as good in those terms, but perform better environmentally. And that really is the essence of refrigerant choice. If we move on and think about R32, which is one of the new fluids being talked about, very good from ozone depletion point of view, better than R134A from the point of view of GWP, has a GWP roughly half that of R134A, operates at higher pressure than R134A. It's kind of halfway to CO2, if you want to think of it in those terms. So it's tougher from a design point of view for pressure, but it gives a larger capacity for a given size of equipment, so it's quite nice that way. But it does have mild flammability. It burns at a fairly low speed. It's one of what are called the new A2L safety class of refrigerants, and the products of combustion are toxic, although the fluid itself, unburnt, is non-toxic. So again, it's filling out the bottom half rather better than the top half. It's also relatively expensive as a refrigerant, but it fits into relatively cheap systems, very similar to the existing R22 systems that we're used to using. One of the new hydrofluoroolefins, the compounds with the double bond that I mentioned, is R1234YF, which has been promoted as a replacement for R134A in chillers, and particularly in car air conditioning. Relatively expensive to make. You're probably talking something that is 5 times the price of R134A and maybe 15 to 20 times the price of ammonia or CO2. But with a very, very low global warming potential, I scored at 9. You could even argue it ought to be 10, and 0 ozone depleting potential. So it fulfills the environmental criteria quite well, but it has this low burning velocity flammability, which, to be honest, is probably fine in very low charge systems, but for use in large chillers or industrial systems, it presents some challenges in complying with the dangerous substances and explosive atmosphere regulations in the UK, because it's classed as a flammable fluid. Again, if we compare it with R12, you can see that it does a better job of filling out the bottom half of the graph at the expense of the top half. And then finally, water. I mentioned there's been some research done on water. At the moment, I would say water systems would be relatively expensive to engineer and would give reasonably poor efficiency. I scored pressure kind of low because water actually operates in a fairly deep vacuum, so presents a completely different set of challenges in terms of pressure. With CO2, the pressure is very high, and the challenge is designing for high pressure. With water, it's probably operating at about 10 to 20 millibar absolute pressure, so very hard vacuum, and presents its own challenges. Gives fantastic capacity, zero ozone depletion, zero global warming, ostensibly non-toxic, but again, that's a question of quantity, and clearly non-flammable. Professor Joachim Powell from the Danish Technical University gave a presentation on water as a refrigerant once, when he said it's clearly by far and away the most dangerous of all the refrigerants that you've seen so far, because it's the only one that's got sharks in it. So that's the thing that you have to be careful with water. As I mentioned, it's under research at the moment. I think when we reach the point where it is in large-scale production and widely used, the graph might look more like this. It's the closest that we get to really filling the circle. Mass-produced water systems could be very cheap. They will be significantly more efficient than other refrigerants, and the pressure, the low pressure, provided we've designed out the technical challenges, will not really be a difficulty. So it's the one that comes closest to really scoring on all fronts. It's a fantastic opportunity once the design has been perfected. However, it has a very obvious disadvantage that it freezes at 0 degrees C. It has a triple point of 0.06 degrees C, so it can only be used in chill applications. It's not suitable for use in low temperature systems. So it's only half the answer, even though it will be very, very good. I want to talk a little bit about the refrigerant numbering convention, because it really is quite obscure. It was invented by somebody with a very, very twisted sense of humor. But once you understand the knack, it's more straightforward than it might look. In this diagram on the screen, the black blobs represent atoms of carbon, and the white are atoms of hydrogen, and the yellow are atoms of fluorine. And this is R134A, one of the refrigerants that I mentioned earlier, the one that was a replacement for R12 in the 1990s. There's a very useful technique when you're looking at these R numbers to figure out what's in the molecule. If you add 90 to the number, then it gives you 3 digits, which are the number of carbon atoms, the number of hydrogen atoms, and the number of fluorine atoms. And this works for lots and lots of refrigerants, and it's a handy way of knowing what you're looking at. The other thing that seems insignificant but is really important is that A on the end, the lowercase a. It means that this is an isomer, and we're talking about the less symmetrical version. If you can imagine that one of the hydrogens was on each end of the carbon stick there, we would have a hydrogen and 2 fluorines on the left-hand end and a hydrogen and 2 fluorines on the right-hand end. That would be R134, which is the symmetrical version. And although it's all the same building blocks, they're put together in a slightly different way, and R134 has different chemical properties to R134A, so that little a on the end is really significant, and it needs to be a lowercase a. I'll come back and talk about that again and again as we go through this. So that gives you a simple rule: add 90 and it'll give you a clue as to what's in the molecule. However, there's a whole bunch of other things that don't follow that system. If the number is in the 400 range, like R404A or R407C or 410A, we're up to, I think, 456 or something like that now. There's a huge number of them. It means that it's a mixture of chemicals, and when it boils, the temperature doesn't remain constant. It has what we call temperature glide. If it's in the 500 series, it's a mix of chemicals, and the temperature doesn't change. These are fluids called azeotropes. Azeotrope just meaning it doesn't change. So 400s will have temperature glides, 500 no temperature glide. It's a little bit less clear-cut than that, because some of the 400 series, like 410A, has well less than half a degree of glide, so it's essentially not changing to any significant extent. And the azeotropes are only azeotropes at one specific point in temperature and pressure, so at other conditions they will have glide, but generally very small, again less than a degree. So there's less of a difference between them than you might think, but in general it's easier to design a system, especially a flooded system, using a 500 series than a 400 series. If it's a 600 number, that's the catch-all, that's the safety net. It's things that don't fit anywhere else. And the most common is butane R600 and its isomer isobutane, which is R600A with a small a at the end. And the reason that butane's in the 600 series, although it's an organic chemical, if you followed the add 90 rule, it would have to be R311T. So there are too many hydrogens basically. It's 4 carbons, 10 hydrogens, no fluorine. So because it would be R311T, it is just R600. There are other fluids in the 600 region, but you probably will never come across them. They're very obscure chemicals. The 700 series is the non-organic compounds. So ammonia is R717, CO2 is R744. These are inorganic compounds where the second and third digits are the molecular weight. So ammonia molecular weight of 17, CO2 molecular weight of 44. There are fluids with a molecular weight above 100, and if they were inorganic, then it would be 7,000 and something. So the only one that comes to mind immediately is sulfur hexafluoride, which would be R7146. But I'm sure that there are a few others out there. If there's a fourth digit at the beginning, apart from the 7000s, for example, R1270, then that indicates that there is a double bond in the molecule, as there is with our 1234YF, which I mentioned earlier. If it's a small a, it shows that it's an isomer, like 134A or 152A. If it's a capital A, then it shows that it's a variant. For example, with 404A, there are several different recipes using the same components. With 407, there are currently, I think, 6 on the market, 407A through to 407F. And I heard recently somebody was talking about 407G, so they've not given up on it yet. They're still making different recipes, but it's the same 3 components, basically. So very important that 404A is a capital A, but 134A is a small a. And 744A, I can think of at least 3 refrigerants that have a molecular weight of 44. CO2 is one of them, as I mentioned, R744. Propane is one of them, but because it's organic, it's R290. And the other one is nitrous oxide N2O, which also has a molecular weight of 44. And now it starts getting complicated. So what about the other stuff? We're seeing more and more complex molecules coming out. So here we've got our 1234 ZE brackets E. Add 90, and it breaks the code for us. It's got 1 double bond, it's got 3 carbons, it's got 2 hydrogen atoms, and it's got 4 fluorines. So that's the molecule for 1234 ZE brackets E. And all that lettering at the back end is letting us know how those components were put together. And it is basically just a code, a nomenclature that you can use to figure it out. If there's a Z as the first letter, that shows that the middle carbon has a hydrogen atom attached to it. If that was a Y, it would indicate that the middle carbon had a fluorine attached to it. And the second letter, the E, shows that the left-hand end of the molecule is an HF, CHF. If that was an F, it would indicate that it was CHH, as we'll see in a minute. And then the really funky part, the capital E, means that this is an isomer, what the Germans would call the entgegen version. Entgegen meaning opposite, or in IUPAC terms and chemistry terms, it would be the trans version of the molecule. And I'll explain what that means in a minute and why it's really important. But just to prove that this stuff really does exist, here's a bottle of it. You can see it's called trans 1333 tetrafluoroprop 1-ene, and it is available and is used as a refrigerant. So we'll talk a bit about isomers because there's two flavors of 1234 being talked about as refrigerants. There's 1234 ZEE and there's 1234 YF. So they're both one double bond, 3 carbons, 2 hydrogens and 4 fluorines, but you can see from the two diagrams at the bottom that they're put together rather differently. Slightly different nomenclature. The 1333 is talking about where the fluorines are located. So there's one fluorine on the first carbon molecule, counting from the left-hand side in the ZE, and there's 333 is the other 3 fluorines are on the third carbon molecule. In the second diagram, there's one fluorine on the second, and there's 3 of them on the third, so 2, 3, 3, 3. And the one in the middle of the tetrafluoropropene is indicating that there's a double bond between the first and the second carbons. So it all means something, but it's a bit complicated. The trans that I mentioned at the beginning of the 1234 ZE is the Entgegen thing. And what that's saying is that the 2 hydrogens between the first and the second carbons at either end of the double bond are on opposite sides of the molecule. So it's Entgegen, it's opposing, it's opposite. We'll come back to that in a minute. And again, it's much more significant than you might think. So here we are, 1 double bond, 3 carbon, 2 hydrogen, 4 fluorine. But look at that, the natural boiling point, the temperature at which the liquid boils at atmospheric pressure is minus 18.1 for ZE, and it's minus 29.4 for YF. Now I mentioned earlier that R12 was commonly used as a chiller type fluid back in the day, back in the 1980s, and R22 is used for lower temperature systems, and I think of them as being very different fluids. But the difference in normal boiling point between R12 and R22 was 11 degrees, 11 Kelvin, with R12 boiling at minus 29.1 and R22 boiling at minus 40.1. So the difference between these two isomers, which are made up of the same stuff, in terms of boiling point, is bigger than the difference between R12 and R22. It really is significant. They are very different and they behave very differently, even though they are made of the same bits and they appear to be stuck together in a very similar kind of a way. And it gets worse than that, because I mentioned before the Entgegen version. There is also 1234 ZEZ, which is the Zusammen version. Again, the Germans got in here. Zusammen meaning together. Again, the same kind of setup, but you can see from the diagram that in this case, with the Entgegen version, the hydrogens are on opposite sides, they're opposing, and on the Zusammen version, or the trans version, sorry, the cis version, they're on the same side. So that's trans 1333 and cis 1333 tetrafluoropropene. And the difference there is that one of them boils at minus 18 and the other boils at plus 9. So the difference in boiling points here is bigger than the difference between R12 and R11. It's really massive. And that's why the letters at the back end are important, because these are totally different chemicals. They behave in a totally different way, despite the fact that they're made up of the same stuff, just put together ever so slightly differently. And there are lots of others. There's 1234YE, so you need to be really careful with the letters in the back to make sure you get what you want. In these cases, one of them boils at minus 22, and the other one, I couldn't find out what temperature it boiled at because it's so unusual. There are actually 7 isomers of R1234 in total, 7 different ways of putting the same atoms together and getting a completely different chemical. So the 2 isomers that are in general use in refrigeration, 1234YF is the preferred replacement for R134A because it gives very similar capacity at a very similar operating pressure for a given application. So that's what's been proposed for use in car air conditioning, the one on the right, with a normal boiling point of minus 29.4. The one on the left gives a much lower capacity, but it gives a rather slightly better operating efficiency. So it's been used in centrifugal chillers as a replacement for R134A, because with the centrifugal chiller you can cope with the change in sweat volume requirement more easily, operating at a lower pressure but giving a higher coefficient of performance, therefore using less energy. So ZEE is very good for centrifugal chillers. YF is preferred for other applications, although if you're willing to buy a slightly bigger compressor, then ZE will give you a better COP, all else being equal, but there's a lot of all else to be equal, so it's not as straightforward as that. And basically, you probably feel it's a bit like this, it's all alphabetic spaghetti, because it's very, very confusing. There's lots of things to remember, and lots of scope for getting it wrong as well. So the overriding message is those little letters at the back make a significant difference. Make sure that you're getting it right. So we talked about refrigerants through from the 1980s to the 2010s, and the question is, where are we headed? On the organic refrigerant side of the chart, HFCs are now being phased out. They were only phased in about 20 years ago, and it's almost like a revolving door. They're on the way back out again. In Europe, they're regulated under the F-gas regulations, and the F-gas regulations originally appeared in 2006 and were then revised in 2014, and they set a fairly aggressive timescale for reducing the quantity of HFC used because of the adverse effect it has on global warming and the greenhouse effect. So by the 2030s, I suspect that if we're using organic refrigerants, they will all be HFO, that HFCs will effectively be a very narrow niche because the quantities will have been reduced so much. And one of the problems with manufactured chemicals like these, if the quantity drops and it drops below economic threshold for production, then it becomes a specialty chemical and the cost of production goes up because it's produced in smaller batches. So as I mentioned earlier, they're already more expensive than the fluids on the right-hand side of the chart, and as the numbers reduce, there is a risk that they become even more expensive. On the natural side, I think water will come in the next decade, and we'll see chillers using water as refrigerant and delivering the fantastic performance that I mentioned, and there's no reason to think that any of these fluids would disappear again. So it's a more stable scenario. I mentioned the F-gas regulations, but the other thing that is now driving HFC phase-out is the Kigali Amendment, as it's called. I've mentioned a couple of times the Montreal Protocol. The Montreal Protocol, full title is Montreal Protocol on Substances which deplete the ozone layer, and that was originally R12, R11, things like that, CFCs because of the chlorine, and included HCFCs like R22, and that's the reason that we've been on this journey in phasing out CFCs and HCFCs. The Montreal Protocol says nothing about global warming, but it has been proven to be a very, very effective method of managing refrigerant phase down. Therefore, when the concern about global warming became apparent, a proposal was made about 8 years ago now to bring the global warming gases into the Montreal method in order that they would be able to phase down in the same way. Global warming is regulated by the Kyoto Protocol rather than the Montreal Protocol, but the Kyoto Protocol doesn't really address the question of phase down, it addresses the question of reducing emissions, because it covers substances like carbon dioxide from power plants or coal-fired power stations and other global warming gases. So Kyoto is better at regulating the amount of emission to atmosphere. Montreal is better at regulating production and consumption of chemicals, and hence there's a strong argument for bending the boundary fence a little bit and bringing the HFCs into the Montreal process. So it's using the same kind of phase out, phase down process as was used for CFCs, and the Kigali Amendment, which is the blue line and the green line on the graph, is following a kind of similar path to the EU F-gas directive. But there are two significant things to note. It's slightly delayed. It was only introduced last year and it only enters into force on the 1st of January 2019. by which time the F-gas restrictions are already started. So it's lagging behind a little bit, but if you look at the bottom of the graph, it actually takes the cut even further than the F-gas regulations. By the end of the F-gas process at the moment, HFCs will be reduced to 21% of the baseline level, but by the end of the Kigali Amendment process, they'll be reduced to 15% of the baseline level. So it's actually more stringent, although it takes longer to get there. And the thing about, it says A5 and non-A5. A5 refers to Article 5 of the Montreal Protocol, and Article 5 lists a number of countries which, because they have what are called developing economies, they are granted some latitude in terms of the dates for phase down. They're cut a bit of slack, basically. And actually, there are more countries in Article 5 than not in Article 5. The developed economies are Western Europe and the USA, but even large countries with a developed economy now, like China and Russia and Brazil, are in Article 5 because back in the early 1980s, when the Montreal Protocol was first drafted, they were deemed to be developing economies. So the difference between the original Montreal Protocol and the Kigali Amendment is that the Article 5 countries originally had about a 20-year leeway. The dates for phase-out of CFCs for Article 5 were 20 years after the non-Article 5 countries. But you can see here the phase-out dates are only a few years apart. The amount of latitude granted is very small until you get down to the 40% level, and then there's a little bit of a delay. So it's basically a recognition that there is a really pressing imperative to do something about greenhouse gas phase down. The other thing that I would point out about this is the first version of the Kigali Amendment, and what we learned, if we learned anything from the original Montreal Protocol process, it was that the dates and the numbers are very easy to change as time goes by. The original Montreal Protocol, which was published in 1986, only talked about reducing CFC consumption to 50% of the baseline level. It never was intended to be a phase-out, but the scale of the problem became apparent, and it very quickly shifted into a phase-out, and then it shifted into a faster phase-out, and then Europe legislated to phase out CFCs even faster. So it moved from a 50% phase down in 1986 to a complete ban by the end of 1999 in Europe. And I have to say, I would not be surprised if the same thing happens with both the F-gas regulation and the Kigali Amendment, and the numbers are tightened and the dates are pulled forward. Basically, if the technology is there to enable the phase out, the political view will be that it is beneficial to accelerate the phase out and happen faster. That's what happened with CFCs. It happened again with HCFCs, and my expectation is it will also happen with HFCs. And the final thing is, I put on the slide that the Kigali Amendment applies everywhere. To date, I think about 135 countries have adopted the amendment. The USA has not, and that's very much in doubt at the moment. But to be honest, I don't think that that will make a massive difference to the process. It will happen, and as I say, I think it will happen faster than the current numbers would suggest. So a few conclusions. The choice of refrigerant is all about compromise and balance, and the graphs give us a really nice picture of where the balances and the compromises lie. Bear in mind that we're looking for something that fills the circle, scores 10 out of 10 in every category, and there is no such thing across the full range of temperatures that we need to operate at. So you are going to be faced with trading off one parameter against another. If you want more efficient, you might have to accept a bit of flammability or a bit of toxicity. The ones that are now a must-have are at the 6 o'clock and 7 o'clock position: ozone depleting potential and global warming potential. So basically, the only fluids that fit the bill on a go-ahead basis by this assessment would be the middle line of natural refrigerants and R1234YF and similar HFOs, which are delivering excellent performance in ozone depletion and global warming, and everything else there is either gone or already or is transitional. So put that into words, I think the pace of change is increasing. We had originally about 30 years to phase out CFCs. That reduced to be only 14 years, but we only have about 14 years to start with to phase down the HFCs, and as I say, I expect that timescale to sharpen up a bit. I can't see that there will be another round of phase down once the HFCs have gone. It's possible that we will discover something about HFOs that means we want rid of them as well, but that would mean adding another axis to my 8-point graph because they score very well on the 8-point graph. So this is probably the last round of phase down, but I wouldn't bet on that because we don't know what else will arise. There are concerns about the flammability, there are concerns about the toxic products of combustion, and there are concerns about the environmental breakdown producing trifluoroacetate in the atmosphere, although at the moment it's in tiny, tiny quantities that are, it's a naturally occurring substance, it's already in the oceans, pretty much universally spread around the world at very low levels, and this activity would not raise those levels by a massive amount. So the question is that something to be concerned about or not? But I suspect this is the last round. In domestic refrigerators in Europe, we've been using hydrocarbons since the early 1990s, and it's been very, very undramatic. It's a kind of unsung success story because there really has been very little to talk about. They're very efficient, manufacture is very straightforward. It is almost impossible to buy a refrigerator in the UK now that does not have hydrocarbon in it. You would have to work very, very hard to do so. And there is really no story there. Occasionally, something will be whipped up in the press about exploding fridges and very dangerous, and usually it's fake news, basically, to use the current term. In the industrial market, the market has switched across to ammonia, did it very undramatically in the early 1990s, and that's been very widely adopted and represents the majority of industrial systems. There are a few cases where hydrocarbon is appropriate in big systems, but they're quite rare, and there are a larger number of cases where carbon dioxide is appropriate, particularly in low temperature freezer plant, where the performance benefit it gives is quite spectacular. So between CO2 and ammonia, the industrial market is pretty well served at the moment. The commercial market with supermarkets is less certain. There are several different strands adopted, some people using CO2, some people using secondary systems, although not so much now, some people using HFOs, and some people using hydrocarbons. I suspect there's an element of horses for courses there, and that variety will remain for quite a long time. The choice for air conditioners is much more difficult because there isn't an ideal solution. The preference of air conditioner manufacturers appears to be to adopt HFOs and to find means of dealing with the flammability of HFOs, mainly through restricting the charge of the equipment. Whether the market will accept that or not is still in debate. There are lots of reasons why that would be a good way to go, but there are some hurdles to be overcome. So the choice for air conditioners is still a little bit less clear. So that brings us to the point of questions and answers, and I can hand back to Tim and ask whether there are any comments in the box. Tim.
A question here from Andy. At what pressure is a refrigerant considered high or low pressure? Is there a threshold?
That's a little bit of a moving target because when I started in the industry, R12 was viewed as medium pressure, R11 was low pressure, and R22 was high pressure. And to put that into context, an R22 system with an evaporative condenser would have a design pressure of about 17 bar. So 17 bar was considered high pressure back in the day. When R404A was introduced, that pushed these numbers up a bit, and it became what you might call very high at about 25 bar as a design pressure for the similar system to the one I talked about. And in context, R12 would probably have been about 12 bar design pressure, but in reality, most people use 17 because it's a big round number in PSI terms, 250 PSI.
So just as with everything else, then we're getting pressure inflation, are we, Andy?
Kind of, yes. But
Okay.
there's good news in the tail, Tim, because after R404A, R410A, and R32 came along, and they're even higher pressure, so the design pressure would be about 35 bar, and of course CO2 takes it to a new level. If you go with transcritical CO2, you'd probably want a design pressure of 120 bar. But what I would always add at this point in the conversation is the high pressure is what delivers all the good stuff about R32 and about R410A and about CO2. It allows you to get a bigger capacity out of a smaller compressor. It makes you less affected by suction line pressure drop, which is a classic efficiency killer. So it enables you to engineer a more efficient system. And the stored energy, because the pipe sizes are also smaller, it can make the installation cheaper. But the stored energy in a CO2 system, small pipe, is probably not any larger than the stored energy that would have been in an R22 system, lower pressure but bigger pipe. So is it more dangerous or not? If the designer's done the job right and used the right numbers, it's not any more dangerous than an R22 system.
Okay.
It delivers a lot of benefit. So what I would say is 25 bar used to be high pressure, but now 120 bar is quite common, and we're well capable of designing and installing systems at 120 bar.
Wonderful. I think that's a really interesting concept to think about, this increase in pressure. Another area that someone's asking is, this is Mark asks, when you were looking at your refrigerant graph, which I thought you might want to call an octet, did you consider oil type and miscibility? And miscibility, can you say what miscibility is? It's the ability to mix, isn't it?
Yes, it's some refrigerants and some oils will mix together, and it's easier to manage the oil when it's out in the system. So, for example, mineral oil mixed really well with R12. We never had to think about oil recovery. It was just dead easy. When R134A was introduced, we couldn't use mineral oil because it wasn't sufficient lubricity, so polyol esters were introduced.
Okay, did you consider this in your octet that you produced?
No, it's not really a hurdle, Tim. I don't see it as a difficulty, but that's probably because I come from a bit of an ammonia background, and ammonia usually is non-miscible, and we have ways of dealing with that. So it's not something that I would consider it in the design of the plant, but it wouldn't have any bearing on whether I picked a refrigerant or not. It's not a big enough difficulty.
Okay, I've got a question here from Anthony. Asks about the possible harmful effects of inhalation of refrigerant. Is there a general rule as to whether they are harmful to health?
They're split in the safety standard, which is ASHRAE standard 34 or ISO 817 is the same content really. They're split into two groups, higher toxicity and lower toxicity, and the words are really quite important. People tend to talk about toxic and non-toxic, but that's not what the standard says. And the threshold between higher and lower toxicity is that the occupational exposure level on a higher toxicity refrigerant is less than 400 parts per million, and on a lower toxicity refrigerant it's more than 400. Mm-hmm. And the thresholds for the old R12, R22s was typically set at 1,000, which is not terribly high. That's 0.1% as the occupational exposure level. But in reality, you could breathe large quantities of them without coming to any harm, provided it was pure refrigerant that you were breathing. It's a bit more complicated because they have other effects. For example, some of the compounds can affect the central nervous system. So They may cause irregular heartbeats or other effects. But that 400 ppm is the threshold between above and below, and the only one in common use that is below that threshold is ammonia, which has a 25 parts per million occupational exposure level. So it really is substantially below the threshold. It's not even close.
Mm-hmm.
It's kind of smelly and nasty to be around. But I see that as a good thing because you know it's there and you know you have to do something about it. So there are occasional fatalities related to sudden release of ammonia, but there are also occasional fatalities related to sudden releases of the lower toxicity refrigerants. Typically where there's a big release, for example, in a chiller plant room, and people are unaware of it, and they go into the plant room and they're asphyxiated simply because there's not enough oxygen in the atmosphere. So there have been some very tragic cases and very sad stories where the first man went in and didn't come back, so somebody else went in to find him and didn't come back, and somebody else went in to find him and didn't come back. Particularly problematic, for example, in the hold of a ship where there's no ventilation at all and it's down in a well, so the refrigerant gathers there. And as I mentioned earlier, CO2, although it's an air refrigerant, has a different effect in terms of toxicity. So it interrupts the breathing reflex. If there's too much CO2, you breathe out, and reflexively you don't breathe back in again, which is clearly a bad long-term strategy. So it's asphyxiation by a different route.
I've got a rider on that question from Wilson. He asks about absorption chillers, but specifically, is lithium bromide considered toxic?
Like all of these salts, it's there's a famous, very old 16th century physician from Switzerland called Paracelsus who said the dose makes the poison, and it's a question of how much. But actually, the refrigerant in lithium bromide absorption chiller is the water, not the lithium bromide. So lithium bromide is a salt. It's not, as far as I'm aware, substantially more toxic than something like calcium chloride, but you wouldn't want to have too much of it around you because it's kind of unpleasant stuff.
Okay, I'll roll a couple of questions into one here. I think one is answered by the second. We're asked by Imran, who's in the UAE, whether two or more refrigerants can be blended to give better performance, and I think the answer to that is yes. And but the second question, which builds on that, is if there were a leak on a R1234ZE system, would the refrigerants themselves separate out into their individual components and mean that the entire charge needs to be replaced?
There's several things packed in there, Tim, so I'll try and pick them off one at a time, and if I miss one, remind me what it was. Anything that's in the 400 or 500 range is already a mixture of chemicals. So R410A is a mixture of R32 and R125, for example. So there's been a very, very healthy industry for the last 30 years in cooking up different mixtures to get different beneficial properties. One of the common wheezes was to put a small amount of hydrocarbon in because it helped with the lubricant return that stopped the lubricant from building up in the evaporator. So there are a lot of blends out there. If somebody was saying, can I mix, I've got a plant with R134A in it, can I put some R1234YF in as well? I would say you have to be really careful because although the two chemicals don't react together in the sense that you would understand the chemical reaction, they influence each other. And that's what the whole thing about azeotropes is about. The boiling point of the azeotrope is not the boiling point of either of the compounds that are in the mixture. They are kind of interfering with each other and playing off each other, not reacting with each other, but affecting each other. So if you were to put something else into your refrigeration system, you would run the risk of changing its behavior quite substantially and in an unexpected way. And one of the unexpected ways is that you can end up with very much higher pressures in the system than you might have expected. And there are some substances that would react, If you were to put ammonia in with almost anything, you would have a reaction.
Okay.
Um,
Okay.
it,
Let's move on.
it,
Can I move on from that, Andy? Just
yeah.
really moving on in to look at whether there is real benefit from such blends. I've got a question from Linda here, and I'll just take a section out of this. She asks, why would an HFO blend such as R449, which has high glides and high cost and A2L safety classification, which I believe means it's mildly flammable,
Yeah.
why would such a blend be used over perhaps R134A, which is low cost, no glide, and A1, which I think no flammability issues at all?
Because it's got a lower global warming potential, and that's kind of the only thing it's got going for it. It scores heavily at the bottom of the chart at the expense of some of the issues further up the chart. So it's I think going to be very popular in the short term, but the components of those 400 series refrigerants in the high 40s and low 50s, a lot of them are going to be regulated under the Kigali Agreement. So they're definitely transitional in that sense, valuable because the way Kigali works is the refrigerant quantity is weighted depending on the global warming potential. So the lower the GWP, the more of the stuff you can have. So when I said 15% of the benchmark level, if the benchmark was entirely R134A and by 2035 we were entirely using R32, which is half the global warming potential, you would actually be able to use 30% of the kilograms of 134A that you'd used, although you were only using 15% of the global warming potential. So these fluids, the R449s and so on, have the benefit of their life will be somewhat extended compared to 134A. However, if the reduction in quantity of the base chemicals results in an increase in price, they could become exceptionally pricey. So it really is an unknown. I don't know which way it will go. I was confidently predicting 7 or 8 years ago that R22 was going to get very expensive, and it didn't. It got cheaper and cheaper and cheaper, and finally it got very expensive, but only in the very, very last days before the phase out. It was much delayed, and it was because there was actually a large overcapacity. The demand had reduced, and basically there was too much of it in the market, so the price didn't go up when you might have expected it. But the reason for choosing it is lower GWP.
Okay, thank you for that. We're just about out of time. Just a comment on that particular question from Marta, just who's chipped in. Just say that R448A and 449A are HFC and HFO blends, which are A1 and not A2L. They're not mildly flammable.
That is correct. Yeah.
Okay.
Thank you, Martha.
So thanks for that. Okay, well, we've still got a whole raft of questions here. Let's just we'll just take one. I think, Andy, we're going to be over time, but I think we got so much interest here. We'll just pick out one more question here. Now, I think this will be close to your heart, and so Brendan's asking here. Could you give any comments on the possible use of supermarkets moving to low charge ammonia chillers with pumped glycol for the chill and freezer cabinets and cold rooms?
Yes, the two thoughts that would immediately spring to mind is it is perfectly possible. It's been done before, anytime over the last 25 years, so it's a possibility. But to be honest, compared to low-charge hydrocarbons in the store, for example, I would see it as being an expensive alternative. So there might be reasons why somebody would want to do it compared to some of the other choices, but it's by no means a universal, fantastic solution for every supermarket. So yes, it's possible, but no, it's not likely to be very widespread.
Okay. Thank you for that. Just another comment here that from Martin, I think a very useful comment, just to say that natural refrigerants are also chemicals, of course, and all are produced synthetically, apart from H2O, of course. And he goes on just to note that flammability is based on ignition energy and flame propagation, but its products of combustion are a completely different subject, and that really builds on what you were saying, Andy. There's more to risk from a refrigerant than perhaps just whether it's deemed poisonous in its native form.